Hi everyone, my name is Amanda Overly and I'm here with Nathaniel Guzman, Angel Zoss, and Nadson Brebrun to discuss integrating kinetic charging into wearable tech and show you what we've been up to. Let's get started. This is our table of contents. Introduction is going to be on slide 1, problem statement, slide 2, background and related work on slide 3, environmental impact on slide 4, technology integration is going to be on slide 5 through 9, tests and results, slide 10, and conclusion on slide 11.
Okay, so this is the introduction. Our project explores energy harvesting and fitness trackers, focusing on durability, convenience, and environmental benefits. We aim to create kinetic-powered smartwatches, transforming movement into electricity for continuous operation without traditional charging, minimizing battery waste, and promoting sustainable technology. It's important so that we can help reduce the battery cost and overall waste of the resources we have on Earth. This approach is also supported by recent studies, including the MDPI's kinetic energy logger research, demonstrating the feasibility and ecological potential of such wearable devices.
Current fitness trackers often need frequent recharging, disrupting the user experience and limiting usefulness during activities like long hikes. This highlights the necessity for trackers with extended battery life to improve convenience and longevity. Additionally, the reliance on conventional batteries in wearables leads to significant electronic waste and environmental harm, emphasizing the need for a shift to sustainable power sources to reduce the ecological impact.
Hello, Professor. My name is Nathaniel Guzman. I'm going to provide a brief summary of the background and related work of our little research project regarding the energy harvesting using piezoelectric materials for a wearable device. Before, there were other studies using other types of energy harvesting sources. You have kinetic harvesting, basically movement, electromagnetic, using the electromagnetic field of the body, electrostatic, using the static electricity created by our body, and triboelectric technologies, which means the use of a tourbillon or other method of generator in order to generate electricity, mechanically generate electricity, so spinning something basically. One of the main problems regarding these methods is that the fact if they require a custom generator or a custom built piece of hardware that needs to be produced in order for the design to be valid or efficient, it increases the cost uh, very significantly. Um, Also, there were other studies done related the optimal placement of and how many of these piezoelectric devices in order for the optimal production of energy, especially doing different type of activities like cycling, running, uh, and how actually to distribute the load of that you're taking out of these piezoelectric devices, because the current that is produced by this device is very small, usually in the microampere range, and the voltage is substantially higher, which means that they're high impedance source. So you need to be careful when you are measuring or doing any type of loading of these devices, because you may actually, by measuring the voltage that you're producing, may actually discharge or use part of that energy that you're generating.
Continuing with the environmental impact, the potential for these devices that can generate electricity for the battery is pretty great. As that would help to greatly reduce the natural resources we use for them, because this would allow you to make them smaller, or you can, in conjunction, you could also not have to replace them as often. This would in turn reduces the amount of natural resources you use, but also allows you to uh, expand, get more out of the resources you have in a sense. So you can create more batteries and more um, devices out of the material out of the materials you saved. This also would allow you to not have to charge at home, which would also reduce other natural resources like copper, as you won't have to have a separate charging cable to charge the smartwatch anymore. Um, another way that we can reduce the environmental impact is by having better integration within the smart devices. having uh, placing like the charging mechanism within the smartwatch itself is a key way. If we can make it small enough, is a key way to help reduce the impact. As it's smaller, it will use less material and it can be more tightly integrated, or even integrated it into the band of the watch itself is another way that we can in, integrate it, and so that we can save on resources. And as a whole, the for the design of the watch, using more sustainable materials and also materials that are more durable and that can be more easily recycled is also like a very important key way that we can make these devices more sustainable as a whole.
Here we explore the seamless integration of technology in our wearables, combining energy harvesting, circuit management, and data logging for optimal performance validated by rigorous system evaluation. At the heart of this system is a compact piezoelectric generator, or PEH, manufactured by MIDE. This particular generator was selected for its compatibility with wearable technologies. One innovative feature of the PEH is its tunable resonance frequency, which we synchronize with the frequency of human activities using neodymium magnets. The images labeled A and B lay out the circuit for this energy harvesting setup. They depict the journey of the energy from the PEH through critical components, like the rectifier and battery charging integrated circuit, ultimately feeding into a low-power Bluetooth-capable microcontroller unit. These components collectively facilitate the transformation of kinetic movement into usable electrical power. Moving on to slide 9, we delve into the intricacies of circuit management. The aim here is the efficient conversion of the harvested AC current to DC, optimized for charging the device's battery. Central to this process is an ultra-low power microcontroller with Bluetooth capabilities, responsible for logging energy data. The strategic selection of components, along with firmware optimization that minimizes energy consumption, is important to the design philosophy. These considerations are crucial for ensuring that the device can efficiently harness kinetic energy, leading to a reliable and eco-friendly wearable experience. On slide 10, we focus on the data logging aspect of the system. The microcontroller unit in question is part of the RFD 771001 module, incorporated into the LilyPad assembly board, which is purpose-built for wearable applications. Featuring a BLE radio and an ARM Cortex processor, the MCU precisely measures the voltage and current from the PEH, relaying this information to a mobile application via Bluetooth. This function provides us with valuable data on energy harvesting efficiency and allows us to understand the charging current dynamics during various user activities. Slide 11 showcases the practical evaluation of the PEH system. They conducted tests involving 10 participants who engaged in physical activities like jogging, documented in figures 6 and 7. We can see energy transfers to battery amounting to 1.75 millijoules to 2.98 millijoules per activity, which is a significant step towards self-sustaining wearables. This translates to an operational time extension of several seconds for the battery after each activity.
Hello, Professor. This is Nathaniel Guzman, and I'm going to give a quick summary and conclusion of what it is or a quick research project. So, wearable devices are only going to increase in numbers in the following years. That's because, in my opinion, that's going to be the new standard that we're going to use to communicate. And it's going to be the new default device that we are going to have instead of a smartphone. I think the next year is gonna we're gonna see maybe not an increase in size of these smartwatches, as an example, but definitely we're going to see an increase of functionality in which having a smartphone is gonna be completely pointless, or we're gonna be like using it like as example a tablet, which is we use a tablet just for content consumption, but not really to actually communicate, especially if these devices are going to have features in them like inclusions of large language models or inclusions or of APIs that allow them to integrate a lot of the application requests that we need to do on a daily basis in the device. An example of these devices is Rabbit, the Rabbit device, which they integrate all the APIs needed for typical operations that you do, like bank transfers, ordering pizza, ordering an Uber, uh, directions, sending texts, doing calls. So all these things that we usually grab the phones to do is gonna be already on a wearable device. So it's just a matter of time. These devices already have a phone numbers. These devices already have all the connected technologies that are needed to integrate very well into the IoT world. So it is important to us to make sure that, especially for some applications in which we don't want to take the device out of out of our hand, or if we do want to take it out and reduce the limit that time that we are not using the device as little as possible. In that case, by having in our case piezoelectric generators will allow us to avoid that charging time, hopefully completely, or reduce it by a significant amount. Because right now, if we see any current iteration of smartwatches as an example, I'm using smartwatches because it's the most relatable of wearable devices at the moment. We see that example Apple devices. Really, the features don't change much, but the size increases. Bigger screens because of the bigger battery that's needed to support long-lasting operation, and to support also the new increase in features and processing power of these devices. So it is up to the benefit of us and the manufacturer, the users and the manufacturers, to make sure that we have an alternate energy production system on these devices. That especially will allow the user to do those activities for a prolonged period of time. In the case, an example is, if you're going to do a hiking trip and you're gonna wear your smartwatch, sometimes you're not gonna have power. You're not gonna have. What if your power goes out? What if your charger that you're bringing with you dies on you, and you don't have any other way of charging your device in order for you to communicate? So you can basically, if with the piezoelectric device, you can just move and then charge the device little by little. So in order for you to have enough energy to make a phone call, as an example. So it will help. This type of technologies will help also in emergency situations, and also it will also help to empower the users to make uh, those activities that they want to do, and to use their smartwatches during those activities that before they couldn't do it because they know the device was going to die eventually. Uh, in our case, of the project and the study that we read for this presentation, the increase in battery life was about 3 to 6 seconds, and that's not a significant number at the moment. But if you compound that over a day or 2 days, or in my case, my example, in my job, I walk 2 miles every day. So somebody like me that's very active is gonna to really use that charging capability to the maximum potential. And probably they're gonna be users, if the system is very efficient, that you won't really have to charge their wearable device as frequent. And also, this technology can be applied to other type of wearable devices, like example, smart clothing, clothing that changes color, stuff like that. That maybe we don't have to really integrate a battery into these devices. They will just be powered by the way we move, especially if we use technologies like piezoelectric materials. An example could be uh, a T-shirt that changes color, and the changing color technology is powered by your movements, or a T-shirt that shows your activity level, or different color based on how you're moving. Those are the type of technology advancements that this technology would allow us to do. And also another issue that this increase in battery life will help is, example, in applications like measuring the heart, measuring the blood pressure. Sometimes there are specific cases. If by case, if somebody has a high blood pressure disease, they cannot really take that out for a significant amount of time. They have to wear the device every day, constantly, because they need to be monitored all the time. So in applications like that, it's really important to have a device that is self-powered. Um, I hope your presentation. I hope you like our presentation, and see you around.